Hey everyone, and welcome. Today we are jumping right into the very heart of C++, and we're going to unpack the fundamental principles of object-oriented programming. We're going to break down all the key concepts that let developers build the powerful, scalable, and manageable software that we all use every day.
It really all starts with this one big question. As programs get bigger and more complex, adding new features can easily become a tangled, chaotic mess. So, how do we manage all that complexity? Well, the answer is in a paradigm, really a way of thinking, called object oriented programming, or OOP for short. It's the strategy we use to bring order to all that potential chaos. So here's our game plan for this explainer. We're going to kick things off with the absolute basics, classes and objects. From there, we'll explore the four main pillars that hold up all of OOP. Encapsulation, which is all about security, inheritance for reusability, polymorphism for flexibility, and abstraction for simplicity. And to wrap things up, we'll check out a few special C++ power tools that make our code even better.
Okay, first things first. Before you can build a skyscraper, you've got to understand what bricks and mortar are, right? Well, in the world of OOP, our fundamental building blocks are classes and objects. Absolutely everything we're going to talk about today starts right here with these two ideas. So, what's the real difference between them? Well, the best way to think about it is this. A class is like the blueprint for a house. It defines the whole layout, the structure, how many rooms, but it's just a plan on paper. It doesn't exist in the real world. An object, though, that's the actual house you build from that blueprint. And you can build as many houses, as many objects as you want from that one single blueprint. And here's the really crucial part. Your computer only sets aside memory when you actually create the object, not when you're just designing the plan. Let's look at a quick code example. On the left, that class student block, that's our blueprint, it lays out what every student needs, things we call data members, like a name or an ID, and what every student can do. Those are the member functions, like enrolling in a course. But it's still just a template. It's that line student S1 that actually brings it to life. That's where we create a real, tangible instance of a student, we call it S1, and now it has its own specific data. All right, let's tackle our first major pillar, encapsulation. Honestly, the best way to think about this one is to picture a secure vault, or maybe a time capsule. It's all about bundling important things together and protecting them from the outside world. So what does that actually mean? Well, it's really a two-part idea. First, we wrap up or encapsulate related data and the functions that work with that data into a single, nice, neat package, which is our class. Second, and this is the most important part, we restrict direct access to that data. We don't want just any part of our program to be able to reach in and change things whenever it feels like. So how do we pull this off? It's not magic. C++ gives us specific tools for the job. We use what are called access modifiers. By labeling our data as private, we effectively hide it from the outside world. This is huge for preventing accidental data corruption. Then, to allow for controlled interactions, we provide special public functions, which you'll often hear called getters and setters. These act like gatekeepers, providing a safe, controlled way for other parts of the code to read or modify our private data, maybe even running some checks before allowing a change. Okay, on to our second pillar, inheritance. Now, if encapsulation was all about protection, inheritance is all about efficiency and code reuse. I mean, why would you reinvent the wheel when you can just take a perfectly good wheel and build upon it? Inheritance basically lets us create a new child class that automatically gets all the properties and behaviors of an existing parent class. For example, you could have a general vehicle class, and from that, you could inherit to create more specific classes like car and motorcycle. The huge win here is reusability. You write the code for has wheels and can move once in the vehicle class, and both car and motorcycle get it for free. You only have to add what's unique to them. Now, this table might look a little intimidating, but just think of it as the official rulebook for inheritance. It tells you what happens to the parent's public, protected, and private members when a child class inherits them. For example, look at the first column for a public member in the parents. If you use public inheritance, which is the most common kind, that member stays public in the child. Simple enough. But if you use private inheritance, that same public member from the parent becomes private in the child. The key thing to remember is that access can only become more restrictive, never less. You can't make something private suddenly public.
And C++ is incredibly flexible with how you can structure these relationships. You've got single inheritance, which is just one child from one parent. There's multi-level, which is like a family tree, grandparent to child. You can have hierarchical, where one parent has multiple different children. C++ even supports multiple inheritance, where one child class can inherit from two or more parent classes at the same time, though you have to be careful with that one. All these options give you a ton of power to design your software just right. Our third pillar is polymorphism. It's a bit of a fancy Greek word that literally means many forms. And honestly, that's the perfect description. It's the ability for one thing, like a single function name, to have many different behaviors depending on the context it's used in. Now, in C++, polymorphism comes in two main flavors. And the biggest difference between them is when the decision gets made about which piece of code to actually run. With compile-time polymorphism, the compiler figures everything out while you're writing the code. But with runtime polymorphism, the decision is actually delayed until the program is up and running, and that's what gives us some incredible flexibility.
So a perfect example of compile-time polymorphism is something called function overloading. This just means you can have multiple functions with the exact same name as long as they have different parameters. So you could have an add function that knows how to add two integers and another add function that knows how to add two floating point numbers. The compiler is smart enough to look at the type of data you give it and automatically pick the right version to call. All of this is sorted out before your program even runs. Okay, but runtime polymorphism, this is where things get really, really powerful. This is all about function overriding. Imagine a parent class has a show method, and a child class redefines that same show method to do something different. If we use a pointer of the parent's type to point to a child object, how does the program know to call the child's version of the function? The magic keyword is virtual. Marking a function as virtual in the parent tells C++, hey, wait until runtime to decide which version of this function to call. And that allows for some amazingly dynamic behavior. All right, let's move on to our fourth and final pillar, abstraction. Now, if encapsulation was about hiding data inside an object, abstraction is all about hiding the messy implementation details behind a nice, simple interface. It's the user-friendly principle. We only show what's absolutely necessary. And this car analogy is just perfect. When you get in a car to drive, you interact with a very simple interface: a steering wheel, some pedals, a gear shifter. You don't need to understand anything about the internal combustion engine, or the transmission, or the complex electronics to make the car go. All that incredible complexity is hidden from you. Abstraction and programming is exactly the same idea. We provide a simple interface for others to use, and we hide all the complicated guts that make it work. In C++, the way we do this is with something called an abstract class. An abstract class is like an incomplete blueprint. It's a contract. It says any class that inherits from me must provide its own implementation for certain functions. And the way we make a class abstract is by giving it at least one pure virtual function. You can always spot these by that unique =0 at the end. This forces any child classes to fill in the blanks, guaranteeing that they all follow the contract and have a consistent interface. All right, we have made it through the 4 pillars. So now, let's look at a few special concepts in C++ that act like power tools for the programmer. These help us manage the life of our objects and handle some special relationships between our classes. Every single object has a life cycle, and what's really cool is that C++ automates the beginning and the end for us. When an object is first created, a special function called a constructor runs automatically to set it up. Maybe it assigns some default values or allocates memory. Then, when the object is done and about to be destroyed, another special function, the destructor, runs automatically to clean everything up, releasing that memory or closing files. It's a fantastic feature that helps prevent really common bugs like memory leaks. Now, this is a super important idea, especially when your objects manage their own memory. A shallow copy on the left is risky. It just copies the memory address of a pointer. So now you have 2 different objects pointing to the exact same piece of data. If one of those objects deletes that data, the other one is left with a useless, dangling pointer, and your program is going to crash. A deep copy, on the other hand, is the safe way to do it. It allocates brand new memory and copies the actual data over, ensuring that each object has its own, truly independent copy. And finally, let's look at 2 special keywords. First, static. This lets you create a variable that is shared across all objects of a class. Imagine you want to keep a count of how many enemies are in your game. You don't want each enemy to have its own separate counter. You want one single counter that they all share. That's what static is for. And then there's friend. This keyword is like giving out a special key. It lets you designate an outside function or even a whole other class as a friend, which allows it to bypass the normal private and protected security barriers in a very specific, controlled way. So there you have it. We've seen how classes are the blueprints, and we've walked through the 4 pillars: encapsulation, inheritance, polymorphism, and abstraction that form the core principles of great design. Remember, these aren't just features of a language. They are a powerful way of thinking about and structuring complex problems. So that leaves us with just one final thought to chew on. Now that you have this powerful blueprint, what complex system will you design first?